Welcome to solverfy.
Okay, in this problem, we're looking at hydrogen, and we're investigating various ratios of occupancy in between the ground state and the excited state, and the first excited state, rather. So we have this increasing ratio, and we're asked to find for each of the cases the temperature that a system in thermal equilibrium would recreate these ratios. So the equation that we're going to be using is the Boltzmann equation, which simply states that the ratio of occupancy for particular states is equal to the E to the energy difference between those states divided by KT, the temperature. So the only constant we need for this problem is the Boltzmann constant, 1.38 times 10 to the negative 3 joules per Kelvin, and we should be able to solve for T. We also, because it's hydrogen, we can use the Bohr model to find the differences, the different energy levels. This would be the Balmer series. And once we have these occupancy ratios, rather, and we can get a corresponding temperature, we can answer some questions about stellar atmospheres. So let's jump into it. Okay, so doing this calculation once, we can use the Bohr model to find the energy levels. Remember that E sub n is equal to negative 13.6 eV over n squared. Thus, for the n equals 1 case, it's simply negative 13.6 eV. For the n equals 2 case, it's 13.6 divided by 4, which will come out to be negative 3.4 eV. So this delta E will be negative 10.2 eV. Okay. So then we can find the occupancy. Well, not find it. We know it. We can relate it to the temperature, which is what we want. Delta E over KT. So doing one or two steps of math, some algebra, move some stuff around, we can get T. Simply negative delta E over K natural log of N2 over N1. So from here, we can plug in the occupancy ratios for parts A, B, and C. K is the same, delta E is the same. We need to convert into electron volts. We need to convert K. So we can use the fact that we can use the conversion factor 1.6 e to the negative 19 joules per electron volt to do that conversion, to convert K into its electron volts version. So for part A, we get a temperature after doing these computations. Get a temperature of 4,275 Kelvin. Pretty hot, but it's only going to get higher from there. For part B, I should probably restate these N2, N1s. So this is for N2 over N1 equal to 10 to the negative 12. Now so if we increase it 4 orders of magnitude and have now a occupancy ratio of 10 to the negative 8, we get a temperature of 6,412 Kelvin. And finally, when we increase it yet again by 4 orders of magnitude, we get a temperature of 12,824 Kelvin. Okay, so let's discuss these results. Clearly, as the occupancy ratio increases, temperature also increases. So we can say that for very, very hot stellar atmospheres with much higher temperatures, there are many, many, many more atoms that are in this excited state, the first excited state, above the ground state. So we could continue this process to find the occupancy into N3, N4, etc. which would produce photons at these different levels, which would recreate the Balmer series. So these lines corresponding to the excited states would appear stronger and stronger as the occupancy increases. Thus, in order to produce this, we would need to have higher temperatures. So this is the explanation for why hot stellar atmospheres will have brighter Balmer lines. There are simply more atoms in those higher excited states to be producing these transitions downward, to be producing the light that we'd expect to see. So that's the main result. Thank you very much.